In this section, we want to learn how to determine the net ionic equation for a precipitation reaction. In the previous section, we learned how to determine the product of a precipitation reaction and how to draw out the overall reaction and balance it. Here we want to take this an extra step, and we realize that these precipitation reactions can be described by three other chemical equations. The first one is the overall chemical equation, and that's what we determined in the previous section, and this is the balanced chemical equation. We've determined the products, we have the reactants, and then we balance the chemical equation. The next one is called the complete ionic equation. This shows all the aqueous ions in their ionic form, and it leaves the precipitate as a solid. Instead of showing soluble compounds in their neutral form, we go ahead and disassociate them into aqueous ions. The last one is called the net ionic equation, and this shows only the ions that react to form the solid precipitate. When we do this, we're going to find out that some ions are not really involved in the reaction. They're not necessarily involved in forming the precipitate. These are going to be called spectator ions because they really do not participate in the reaction. They are included in the complete ionic equation, however, they will not be included in the net ionic equation. So the steps to determine the net ionic equation for precipitation reaction starts with determining the formula of the precipitate, then writing the overall balanced chemical equation, determining which of the reactants and products are soluble, and then writing down these soluble compounds in their dissociated ionic form. Remember, during this process, the precipitate is considered a solid and is insoluble and is not dissociated in this particular step. When we're done dissociating the soluble salts into their ionic form, this is called the complete ionic equation. Then we will subtract off ions that appear on both sides of the reaction arrow. So remember, a reaction arrow can be equated to an equal sign in an algebraic equation, so that if we see the same thing on one side of the reaction arrow and the same thing on the other side of the reaction arrow, they can be canceled out. After we do this, what is left is called the net ionic equation. The ions were removed during this process are going to be our spectator ions. So here's an example. We have two aqueous solutions of sodium hydroxide and barium nitrate. These are mixed and in precipitate forms, and we want to know what the net ionic reaction is. The first thing that we want to do is find the precipitate. So we look at our two reactants and determine what ionic species they form when they are dissociated. So sodium hydroxide dissociates to make Na plus and OH minus. Barium nitrate dissociates to make barium 2 plus and nitrate. We recombine the ions, so we take the positive from one and the negative from the other, positive from one and the negative from the other. We recombine these ions to form our two products. Na plus and NO3 minus have the same charge, so they are recombined to make sodium nitrate in a 1-to-1 mole ratio. Here, barium is 2 plus and hydroxide is minus 1. So this will recombine to make barium hydroxide. And because hydroxide only has a negative charge, we will need 2 hydroxides. Between these two now, we have to determine which one is the insoluble salt. Sodium nitrate is listed as being soluble in Rule 1. Barium hydroxide is shown to be insoluble, so our precipitate, our product of this reaction, is barium hydroxide. Then we write the equation out. The two reactants were given. The two products we determined. The subscripts are important. In our two products, sodium nitrate was determined to be soluble, so it is written as aqueous. Barium hydroxide was determined to be a precipitate or insoluble, so this gets the S subscript. Then we balance the reaction, and we've talked about this previously, and we get to our first reaction. So this is the complete balanced reaction. Next, we want to find the overall ionic reaction. And to do that, we disassociate the soluble compounds into ions. This means soluble compounds are written in their dissociated ionic forms. The precipitate, which gets the subscript S, is not dissociated. Here, this gets a little tricky. You need to watch out for subscripts and stoichiometry because these are going to come into play when we write out the ionic species. Remember, after dissociation, the only species with subscripts should be polyatomics. So we start from the left. We have sodium hydroxide. It is soluble. When this dissociates, it goes to make 2 Na plus and 2 OH minus. So there's one sodium and one hydroxide, but the stoichiometric 2 comes into play, which says that I have 2 sodiums and 2 hydroxides. Barium nitrate dissociates into making barium 2 plus, and it also dissociates into making 2 nitrates. So this subscript 2 in the molecular formula says that we have 2 nitrates inside of barium nitrate, and so this needs to be shown in our complete ionic equation. Sodium nitrate has a stoichiometric 2, so this means that it dissociates to make 2 Na plus and 2 NO3 minus. And then barium hydroxide, because it's a solid and our precipitate, it is not dissociated. When we're done with this, we have the complete ionic equation. So we have taken all the soluble species and we have drawn them in their ionic form. In the last step, we want to find the net ionic equation. To do this, we cancel species on both sides of the arrow, and this will get us to our net ionic equation. Inside of our complete ionic equation, the reaction arrow is equivalent to an equal sign, so look for species that are both on the left and the right of this arrow. The first one we notice is 2 Na plus. There's 2 Na plus on the left-hand side of the arrow, there's 2 Na plus on the right-hand side of the arrow, so we can cancel those. The other one is 2 nitrates. There's 2 nitrates on the left-hand side of the arrow, there's 2 nitrates on the right-hand side of the arrow. These can be canceled. These species that we just canceled are considered the spectator ions. So for this reaction, Na plus and NO3 minus are the spectator ions. What is left is the net ionic equation. So after we're done canceling, we have 2 OH and barium 2 plus on the left-hand side of the arrow, and we have our product, barium hydroxide, on the right-hand side of the arrow. And in reality, when you're done, the net ionic equation really should be the ions going to make our product. Our product is barium hydroxide, so I would expect the net ionic equation would be ions to go to make our product, which is barium 2 plus and 2 hydroxide. So you can kind of check your answer to see if you've done it correctly. So the net ionic equation should be ions going to make your insoluble salt. Once again, if you have any trouble during this process, you've probably made a mistake in creating the product or disassociating ions. Some of the major mistakes I've seen are not combining the ions for the product in correct ratios. So say if I had barium 2 plus and OH minus and I want to combine them together to make our product, and I combine them in a 1:1 mole ratio, this is incorrect because barium is 2 plus, hydroxide is 1 minus. This would not be the correct way of combining them. The correct way of combining them should be barium and 2 hydroxides. Another problem I normally see is not disassociating a ionic species completely. Here, barium nitrate should be disassociated to make barium 2 plus and NO3 minus. What I mean by not disassociating completely is it's very common to keep this part together and not disassociate it, and keep the 2 nitrates as a whole unit and keep the subscript 2 and give it a -2 charge, when in reality these should go to make 2 nitrates, like what we did up here. Barium nitrate should disassociate to make 2 nitrates. It should not stay combined to form this species. Another common mistake is not including the stoichiometry during dissociation. So here, if I was to dissociate sodium hydroxide, it's a very common mistake to forget the stoichiometric 2 and just say 2 sodium hydroxide disassociates to make Na plus and OH minus. In reality, I need to have 2 sodiums and 2 hydroxides. Because I have a stoichiometric 2, that means I have 2 sodium hydroxides, which disassociates to make 2 Na plus and 2 OH minus. Kind of the last problem is giving the incorrect charge during dissociation. So when we were talking about nomenclature, being able to determine the charge on a species is very, very important. So we either get it from whatever ions are attached or from the periodic table. This is a very important idea, and we talked about it quite a bit during nomenclature, so if you need a review, you can look at that. But a common mistake is to say take barium nitrate and disassociate it into Ba plus and 2 NO3 minus. In reality, barium is 2 plus. I know that because it's in the second column of the periodic table. I also know this because it's attached to 2 negatively charged nitrates. So if you leave it as barium plus, you're going to have problems during this reaction. And this mistake is very common with transition metals. Remember, transition metals have variable charges, and really we have to look at the counterion to determine the charge on a transition metal. So a mistake here would be to take iron 3 nitrate and disassociate it to make Fe2 plus and 3 nitrates. In reality, it should be 3 plus. And so if you do this, if you leave it as 2 plus, you are going to get the wrong answer when you get down to the net ionic equation. And just remember, this whole idea of what charge a particular species has was covered in great detail during the section of nomenclature, so you might want to review that.